Hello everyone, in today's video we are going to go through IChO 2024 problem 8. So problem 8 is made up of 3 parts. 8.1 which deals with the first synthesis scheme, so we have to draw the structures of compounds A to E. Then for the second part we have to draw the structures of compound F to K from the second synthesis scheme. And finally we have one last part to draw the structure of compound M. So let's take a look at the first synthesis scheme and how we can get compounds A to E. So let's take a look of the process from the starting compound to compound A. Let's take a look at this process. So here we have an electron-rich benzene ring. We have an electron-poor carbonyl group. So what's going to happen is that the benzene ring, the electron-rich benzene ring, will attack this electron-poor carbonyl carbon, resulting in this bond pair becoming a lone pair. So once this lone pair comes down, it will kick out the good leaving group, that is chloride. And because of that, we will have an acylation to the benzene ring. So as we know, OMe is a 2,4 directing group. So the acylation would occur at a second or the fourth position. However, because these two positions are the same, we are just going to pick any one of them, and we can add the acyl group there. So what's the purpose of zinc chloride? Well, the zinc chloride is actually a Lewis acid, so it will act as a catalyst to make this reaction proceed faster, and we can get our compound faster as well. So this is compound A. Now what happens from compound A to convert it to B? Well, to really figure out what happened, we can take a look at this intermediate that is given to us. In this intermediate, you can see some resemblance to compound A. So this resembles compound A, and this part resembles this compound. So between compound A and this compound, we can also see a CC double bond. So where is the CC double bond? Well, it is in place of the CO double bond present in this reagent. So that is highly suggestive of an aldol condensation. And because of this KOH here, we can be quite sure that an aldol condensation has occurred, because KOH is actually a strong base that can remove this acidic hydrogen. So if I draw the mechanism, it will be something like this. I'll just represent this with AR. So the OH minus, the lone pair, actually comes in and grabs this acidic hydrogen, and then you will form an enolate ion. So this enolate ion then attacks, okay, I'll represent this with AR as well. So you have your aldehyde here. So this enolate ion can then attack this carbonyl group, which is highly electrophilic. So please take note to count your carbon really carefully. So this is your O minus, this is your AR group. Okay, now we also have water present also, right? Because you have your H2O formed here, and so this lone pair can then grab a H plus from H2O to give back your KOH. So the KOH here is actually a catalyst. After this, you will have this. Now, if another OH minus comes in and grabs this acidic proton, you can have this. So you form an enolate again. However, here when the lone pair comes down, you can kick out this hydroxyl group, and that will give you your compound B. So let me draw compound B here. Sorry, this should follow compound A. OME, OME, OME. And for the rest of the structure, you can just copy this. So that will be your compound B. So what happens from compound B to this intermediate structure is just that the AlCl3, which is a Lewis catalyst, which is a Lewis acid, it will cause this OMe group to be deprotected, giving you back your OH group. So what happens from this intermediate structure to compound C? So here we can make use of the formula given to us here. So in this compound, we can count the number of carbons. So there are 6 carbons here, 6 carbons here. So 12, 13, 14, 15, 16, 17, 18. So there are 18 carbons in this intermediate compound. However, there are only 17 carbons in structure C. So what happened? We can read the hint here. C has a tricyclic system and it has the same number of hydroxyl groups as the compound preceding it. So from the loss of one carbon, we know that one of these methyl groups is probably deprotected. But what happens after the deprotection? Well, the second sentence here tells us that the number of hydroxyl groups stays the same. So nothing happened here. So this, you will see this hydroxyl group in C as well. So what happens is that one of these must have gotten deprotected and reacted away so that we didn't produce an additional OH group. So which one is it? Well, we can take a look at the final structure given here. In the structure given here, we see 3 rings. So one of these rings is probably formed from the step of this intermediate structure from its conversion to structure C. So we know structure C has 3 rings, and these are probably the 3 rings that we're looking for. Then we know that we find that there's an oxygen here. So the oxygen is probably from here. It probably reacted to form the ring after the deprotection of it. So we can just copy down this final structure. We know nothing happened to this hydroxyl group, and we know nothing happened to this one as well because the number of carbon didn't change further. However, we know something happened to this one that I'm drawing. So we're just going to draw the 6-membered ring because the double bond is still here, so no reason to make it go away. And also we know this group didn't get changed as well because the number of carbons didn't change. So this is probably structure C. To verify it, we can check the double bond equivalence in structure C. So how you check the number of double bonds or rings that is present in a structure is that you multiply the number of carbons by 2, then you plus another 2, then you minus the total number of hydrogen and halogen atoms, and you divide it by 2. So 17 times 2 is 34. So this is 36. 36 minus 14 is 22. And 22 divided by 2 is 11. So you should have 11. The total number of double bonds as well as rings is 11. So we have 1. Let me change color. So we have 1, 2, 3 rings. So you should have 8 double bonds. So 1, 2, 3, 4, 5, 6, 7, 8. And that shows that our structure is correct. You can check the number of oxygens as well. So 1, 2, 3, 4, 5. So that gives us a confirmation that we have gotten the correct identity of C. Now what happens from C to D? The step C to D is necessary to avoid any unwanted reactivity with DMDO. Well, we haven't seen DMDO we probably haven't seen it before, but the question also tells us that DMDO is a hydroxylating agent. So we can actually work backwards from this step onwards to figure out what happened here. So compare the structure of the final product with C. What's different? Well, the structural difference that's very obvious is this OH group here. So what added this OH group to structure C is probably the step from D to E. So from D to E, this OH group is added. Then what happens from E to this final product? BBr3, haven't we seen it before? Well, it is kind of similar in structure to AlCl3. And because of that, we can deduce that its role is probably a deprotecting agent. So we see we have many hydroxyl groups here. However, we have a lot of OMe groups here. So something must have happened to deprotect these oxygens to return it to a hydroxyl group. So what did that job is probably BBr3. And because of that, we can deduce the structure of E. So the structure of E is probably this final product, but with methyl groups instead of hydrogens. So with all these information, we know that from C to D, what gets added is probably a methyl group. So where can a methyl group be added? Well, the only answer is here. So structure D is this structure. Now, we know that from D to E, let me just use green color. From D to E, an additional OH group is added. That's all. Then from E to this, all the OMe group gets deprotected. So that will give us our solution for part 8.1. Now let's move on to part 8.2. So we're going to look at another synthesis scheme. So let's just look at F first. So what happens from this to F? Well, we have a weak base, K2CO3. So where in the starting material or reagent is acidic that will react with a weak base? Well, we have a phenol group here. So the phenol group is mildly acidic. So this H will get deprotonated. So this phenol group will get deprotonated and the H will be removed. And this O minus will then be free to substitute away this Br minus, which is a good leaving group. And because of this, structure F will just look something like this. So that's what structure F will look like. My apologies, I counted my carbon wrongly. So you see, this is 1, 2, 3, 3 carbons. I drew 2 just now. So yeah, another reminder that please keep that carbon tracking is really important. Please remember the number of carbons and remember to check them before proceeding. So this will be your structure F. Now, structure F to G. This step has a lot of reagents, and that is kind of scary, but that's okay. We have a hint. G is a bicyclic compound with one of the rings being a heterocycle. So a heterocycle is just a cycle with something that is not carbon, or yeah, something that's not carbon. So in this case, it can be deduced from this structure that this heterocycle that they're talking about is this heterocycle. So let's think about what might happen from F to G. So how does this heterocycle get formed? Well, we see that we have the nitrogen is ready for us here. And we also have a methyl group. So what we're missing is actually just one carbon here. So where does that one carbon come from? Well, that one carbon looks like it will come from here. So G would just be F, but with this part. Okay, so let's just copy down this structure. But we don't have a tosylate group here, so we're just going to put H here for now. We'll check if that's correct later on. Okay, we can just draw our benzene ring. Of course, we must follow structure F in terms of the substituent placement. And yeah, so far so good. It looks alright. Looking at this more, we know that the tosylate group actually came from the G to H step. So the G to H step would just be removing this H and putting in tosylate instead. So that would be your structure H. Now what happens from H to give you this compound? Well, what happened to H is that a rearrangement reaction occurred. So see, this part went here, and you have a OH group here instead of this huge substituent. So it's just rearrangement under heating. Yeah, even the hints told us that. So the hint said H isomerized upon heating in the presence of the amine base. So yeah, so we know the molecular formula of H and this structure are the same, so that will help you in checking as well. Now, what happened from this structure to give you, what happened from this structure to compound I? Well, we had K2CO3 again. Doesn't that look familiar? Well, we have K2CO3 here as well. So the same thing happened. This H got removed, giving you a good nucleophile to attack this, making the Br leave. And that will give you your compound I. So we just have to draw it here. Everything else remains unchanged. Please don't forget a substituent. Remember, there's an additional carbon here, don't forget about it. So that will be our structure I. So from I to J, we have OSO4 and NMO. So NMO looks like this. And its role is actually a co-oxidant. So OSO4 is oxidizing, but it's very expensive. So that's why you need a co-oxidant to reduce the amount of OSO4 that you have to use. So this is actually quite a famous reaction. So what happens is actually a CC double bond will be converted to a dihydroxyl group. So this bond will be removed, giving you OH, OH, and that will be our structure J. From structure J to K, again we're given a lot of reagents, and that's kind of confusing, but that's okay. When you see this, it looks like an oxidation reaction, and the hint actually tells us that K is a product of an oxidative cleavage of the newly formed functional group in J. So what's the newly formed functional group? It's this. And K has a 1H NMR signal at 12 ppm. At 12 ppm, that strongly suggests carboxylic acid. So the carboxylic acid will actually have hydrogen here and a ppm, and the chemical shift will probably be near 12 ppm. So here K will probably just look like this. So the cleavage must happen here, because usually when you hear something like oxidative cleavage, it's usually a CC bond that gets cleaved, and then because of the oxidation, this will just become a carboxylic acid. So yeah, it will look something like this. Oops. So that will be our structure K. So you might ask, can't you just do a one-step oxidative cleavage from a CC double bond using something like KMNO4? Well, the answer is, in real synthesis, you probably want to have high yields, you don't want a lot of side products, and putting in such a strong reagent such as KMNO4 instead of doing a two-step, a milder synthesis, that might mess up your reaction mixture. It might cause you to have a lot of side products, and that's generally not good. So you want to have something that's mild and specific, that will only attack where you want it to attack. So that's why you do a two-step oxidative cleavage. So yeah, I to J, this step is just setting up for what's to happen in J to K. Okay, so we're done with 8.2 as well. Let's continue with part 8.3. So for part 8.3, we are going to elucidate the structure of compound M. And there are several pieces of information that we know about M. First, that M resembles this, the core structure of this. Second, M resembles L because it comes from L. Third, M has 10 distinct proton signals while L has 11. That means although M is bigger than L because it resembles this molecule, M has some kind of M has a certain degree of symmetry that allows it to have less proton signals than L. So M looks like this. M contains this, and M is symmetrical. So these are the three pieces of information we have about M. Okay, now the second thing we can do is to compare the structure of L, which is this, against the structure of this molecule, because M will resemble both. So let's first talk about the linkage here. Linkage is here, and the question purposely showed the stereochemistry of this carbon. That resembles both this and this. And upon closer inspection, you will find that this molecule is actually symmetrical as well. So it's symmetrical both here and here. So you might say that these two actually are not exactly the same, but they are symmetrical because of resonance. Now we can just count the number of carbons in a chain. So we have 1, 2, 3 carbons in between, and here we have 1, 2, 3 carbons as well. And actually, if we look at all the other groups, they actually resemble the groups here. So let's just hypothesize that M looks exactly like the core structure here, except for these two groups. That will allow us to draw the following structure. We'll talk about where to place here later. So OH. So basically you just copy this part down. Okay, now where to put here? Well, you can see that this right part actually resembles L, so you can just copy down the stereochemistry of L. However, forming this part requires us to turn this molecule around 180 degrees. Therefore, OAC will be here, while ET will be here. So that is probably our structure M. However, let's check how many NMR signals it has. So it has one here, one here. Let me change color. One here, one here, one here. One, two, one. Oh, sorry, I made a mistake. This is supposed to be OAC. One. Yeah. So we have 1, 2, 3, 4, 5, 6, 8, 9, 10. So we have 10 signals. Then because of symmetry, the rest of the signals here will just be the same as these. So that pretty much assures us that we have gotten the correct answer, because yeah, truly it resembles both this as well as this. So that would just be the best answer we can give for part 8.3. And with that, we have reached the end of this video. Thank you so much for watching, and please come back for my next video. Goodbye.